Good morning, everyone. I'm Ahana,
And I'm Sai.
and our project is called AquaScan, which is an AI-powered system that can protect ocean microplastic contamination instantly from GPS coordination and dates without the use of boats or labs and waiting. Are plastic particles that are smaller than 5 millimeters. They're invisible to the naked eye, but they are also everywhere. 8 million tons of plastic enter our oceans every single year, with over 700 marine species being affected. The core problem is that detecting microplastics today requires manual microscope analysis and/or expensive lab equipment and experiments. This means that large-scale monitoring is slow, costly, and inaccessible. Scientists can't monitor the whole ocean, and policymakers have no data, which means the problem keeps getting worse. Our goal was to build an AI system that could do this monitoring instantly, affordably, and at scale. We broke the big problem down into six sub-problems that will exist today. Firstly, there's no early warning system, which means we can't flag a high-risk ocean region before spending hundreds of thousands on sampling voyages. Second, manual lab analysis takes weeks per batch, which is far too slow for real-world monitoring. Next, historical survey data is scattered across decades and institutions. It's almost impossible to detect trends without computational tools. Fourth, existing tools are location blind, which means they don't use the fact that ocean gyres physically concentrate plastic into predictable hotspots. Next, without concentration estimates, we cannot assess the health risks to marine ecosystems or to humans. And lastly, there's no real-time prediction API. No tools exist today where a researcher can type in coordinates and instantly get a contamination risk score. But our model, AquaScan, is able to address all six of these gaps.
So the facts, stats, and impacts. Basically, 53.7% of samples of water that were collected in our data set were positive, aka they had a lot of microplastics. And the highest amount of microplastics that we found was 12.3 million pieces per kilometer squared, which was the biggest in the overall data set. And so we had 26 years of ocean data within our data set. And as you can see from this graph, it starts pretty low overall in 1986. It slowly rises all the way up until 2012, where it's strenuously high. And then in total, we had 7,755 sampling locations. So the key impacts of microplastics and like their effects within the environment is that they leach toxic chemicals such as BPA and phthalates into marine organisms, and this harms them. Small fish ingest plastic pellets, concentrating toxins up the food chain to humans. So humans will eat basically the fish, and that'll cause them to also experience the effects of eating the microplastics. And then ocean gyres accumulate the plastic into quote unquote patches, which essentially just are incredible like spans where there's a lot of microplastics. And it's detected in 114 aquatic species that are sold for like eating, which is the same thing essentially as two, but it shows you the scale of it. And then for the fifth one, the estimated economic damage to marine industries is about $13 billion per year globally. So our proposed solution is that like we would rather rather than wait weeks, we would rather take lab results from physical water samples and train like a model to see if the microplastics are present in the water based off of the location and like the day. Basically, for the first stage, we used a binary classifier, which just has the random forest model determine if it's yes or no in a certain location and the day. And then stage two, we had the concentration estimator, which is basically just estimating the actual concentration, which is self-explanatory, I suppose, of the microplastics and in the water. And then the advantage to having be an AI is that the AI can produce a prediction very quickly, and you don't have to actually wait and send it back to a lab or any sort of tests run on it. So any researcher can query it with a GPS coordinate.
There were 6 steps through how we built the pipeline. So first, we defined the problem precisely by framing it as 2 separate machine learning tasks, a binary classification for detection and a regression for concentration estimation. And then we collected the data and validation. So we loaded our data set and we checked for missing values, validated the geographic ranges, and then confirmed the class bounds, which was 53.7% positive samples. Then we feature engineering, where we parse each data into year, month, season, day of year, which gave the model temporal patterns to learn from. And we also log transformed the target variable to handle those outliers. Then our step 4 was to train test split, where we stratified 80-20 split with a fixed random seed of 42, so our results were definitely reproducible. And then step 5 was training the model on all samples and having a separate regressor trained for only the positive, which were the contaminated samples. And then for step 6 was evaluating. We measured the accuracy, and we used 5-fold cross validation to confirm that the model generalizes beyond training data. Um, Next, for the data science collection and exploration, this was the data we worked with. Our data set came from the NOAA, which is the National Oceanic and Atmospheric Administration, which is a federal scientific and regulatory agency. And it also comes academic ocean trawl surveys. It contains 7,755 sampling events across the globe, and it spans from October 1986 to December 2012. Each row has 4 columns, the date, latitude, longitude, and the microplastic count in the species per kilometer. The concentration values are skewed, which means the median positive sample has 540 pieces per square kilometer, but the max is over 12 million, which is why we applied a log transform. And the feature importance chart on the right is one of the most interesting parts, because the longitude accounts for 34% of the model's decisions, and the latitude accounts for the other 26, which means together this location explains 60% of all of the predictions. This confirms that plastic concentrates in predictable places are driven by gyre geography and ocean currents, and this was already known by scientists, and this model learned directly from this data.
So what is a random forest? So it's basically just an ensemble of decision trees. So multiple, or in this case, 100 individual decision trees are each trained on a random section of the data. And so each tree votes on the outcome, and they either say yes or no. So bootstrapping aggregating is just, it can be simplified to bagging, and basically each tree sees about 63% of the training data, which is completely random, and it reduces variance and it prevents overfitting. So this is an ideal type of model. Additionally, it has feature randomness, which is basically when at each tree split, only the square root of n, so in terms of n data, features are considered. So it forces trees to be different and captures multiple different patterns and possibilities. And then the final prediction is just a majority vote. So whichever one the majority of the trees vote for is what the overall decision will be. And it's pretty average. It's pretty much the average, and it's robust to all noise and outliers. So the classifier config is basically where we put like we put 100 individual trees, and then the feature randomness is essentially where the max features is just the square root. The min sample leaf we did is 2, and the random state was 42. These essentially are just basic ideas that we change. And then the end jobs is -1. Target is basically you want it to say like 0 or 1. And then the regressor config is essentially the same thing, except that the training data and the target, they're slightly different, where the training data is only positive samples, and then the target is log 1 plus pieces per kilometer squared. So the technical details of the solution. So we used Python 3, NumPy, Pandas, scikit-learn, matplotlib, and argparse. So the pipeline steps. So first what we did is we loaded the data, and we did this from the marine.csv. And then we did engineer features, which is essentially just parsing the data. And then we split the data so that we had 80-20 split in order to properly train and test it. And then a train classifier, so we did an RF classifier on all the samples. And then a train regressor, which is just an RF regressor on positive samples only, though. And then we evaluate the models, seeing their accuracy, and we also write the confusion matrix. And then we use predict single in step 7 as a two-stage inference to classify and regress. So the model evaluation metrics, basically it's has a 71% accuracy and a 74% precision score. And the CLI usage is essentially where we just showed the code to sort of demonstrate it.
Okay, so the model, let's look at the model what actually does on the test set. There's 1,551 unseen samples, and there's 481 true negatives, which means that the model correctly identified clean water. And there's 626 true positives, which means that the model correctly identified contamination, which is what the model is good at doing. There was 254 false positive, which means that clean water was flagged as contaminated. In a real world situation, a false positive means that we investigated somewhere unnecessarily, which is an acceptable cost to comparing as a false negative. There was 201 false negatives, which means that a contamination model, the model missed some contamination, which means we're working on what we're working on to reduce in future iterations. Then we can show the results.
Okay, so conclusion. So what is proved? So it's proved that machine learning could actually detect the microplastics using just the location and the date of time. And it also shows that like the random forest model that we use achieved like a 71.2% accuracy, which is honestly pretty high. And then the location is it really it plays a key factor into the predictions. And if you know where the location is, then of the water sample, then it's pretty easy to tell where it is. Uh, and then two-stage pipeline is a lot more effective than a single model.
For future directions, we want to add richer environmental features, like adding ocean current speed, sea surface temperature, distance to coastlines, because these will significantly improve the model's accuracy. We're also exploring the XGBoost as an upgrade to better handle the extreme concentration of outliers in the data. And our biggest future goal is to make real-time web application, which would be a map interface where researchers and policymakers can click on any ocean current coordinate and instantly get a contamination risk score. And we need post 2012 data because pollution has risen dramatically in the past 13 years. and restraining on current data would make this system far more actionable. So AquaScan demonstrates that AI-powered environmental monitoring can be fast, scalable, and accessible. The ocean is too large to monitor manually, but with machine learning, every GPS coordinate on Earth can have an instant contamination risk score. Thank you.
So now I'm gonna show like a small sample of like the data. The data that we got. Okay, so essentially the microplastic detection. This is the machine learning pipeline results. So a lot of the concentration in the samples was kind of closer to being skewed, and the random forest was often better than like a random baseline. So the importance of this, you can see that it has a 35%, and for the longitude and the latitude is a 24%, and the year is an 18%. Everything less is about like it's not as effective. And then the regressor, so the line of perfect prediction and what we want to see, but the actual like predictions that the model gave were the ones in the blue. So it was overall kind of closer to the bottom. And this is the confusion matrix that we saw earlier. It basically shows like if the true label was actually clean, then how many did the model predict clean and how many did it detect wrong. And this is the temporal trend, which essentially shows that around 2007, uh, the mean pieces per kilometer square sort of rises. And this is the geospatial distribution of the microplastic samples. So essentially, what this is telling you is that for the latitude and like the log and the amount of pieces per kilometer squared, the clean and the detected, and it shows like the distribution of it throughout like each location, sort of. And that's all. Thank you.